for this problem, we have an experimental device that imparts a force of magnitude 47 pound to the front edge of the rim here at A. To simulate the effect of a slam dunk, we want to determine the moments of this force about point O, down here at the base of the basketball goal, where the post attaches to the ground, and then about point B, which is at the attachment point for the backboard and the support post. And then last, we're asked to locate a point C on the ground relative to this base point at O, where the force imparts no moment. And that will actually be a very easy calculation to do. All right, let's zoom in here to where we can see a little bit better. So we know that F is equal to 47 pounds. Now, I'm going to go ahead and sketch the components here of F. It has a horizontal component, and it has a vertical component. And one nice thing about this problem is we have a 3, 4, 5 triangle here for the slope of F. So we know the horizontal component is 3/5 F, and the vertical component is 4/5 of F. All right, let's decide on a direction to take moments as positive. I'm going to take counterclockwise positive. This is entirely arbitrary. You could take any direction you wanted as positive. Typically, we think of counterclockwise as positive, but don't be locked into that. Okay, so let's start by taking a moment around B. So the moment around B is equal. The vertical component is going to act through a 28-inch moment arm to produce a clockwise moment, which is negative in my system. So that's a minus 28. And I'm going to go ahead and divide by 12 so that we're going to compute our moments with units of pound-feet. So I know these dimensions along the top here, and this 12-inch are given in inches, but I'm going to go ahead and divide by 12. So minus 28 over 12, and then the vertical part, which is 4/5 of F. The horizontal component, which is 3/5 of F, acts through a 12-inch moment arm to produce a clockwise moment, so also negative, 12 by 12, and then 3/5 of F. And we could substitute here, so 28 over 12, and 4 divided by 5 times a 47-pound force, and then minus 12 by 12, and 3 divided by 5 times a 47-pound force. And what you would find is that the moment around B is equal to 115.9, and you get a minus sign with it, pound-feet. And so we could write this as MB is 115.9 pound-feet clockwise, and that is our moment. So again, just remember, vertical components need horizontal perpendicular distances, and horizontal components require vertical perpendicular distances. And obviously, if it's horizontal, vertical is perpendicular, and likewise for a vertical force, horizontal is perpendicular. Just be careful. I see a lot of mistakes made with that. All right, let's compute the moment around O now. So the moment around O is equal. The horizontal component acts through a 10-foot moment arm around O. It's going to produce a counterclockwise moment, which is positive. So we have 10 feet. And be mindful of your units here. We're going to have feet and inches. The vertical component acts through this total horizontal distance of 36 plus 28 inches to produce a moment around O. And so we would write that, it's a clockwise, okay? So that's a minus, and we'll write 36 plus 28, divide by 12, and then multiplying 4/5 of F. And we can substitute, so we have 10 times 3/5 of 47, and then minus 36 plus 28 by 12, and then 4/5 of 47. And if you do the math here, the moment around O turns out to be a positive number, 81.5 pound-feet for the units, and the positive sign tells us that it is a counterclockwise moment. So that's relatively easy. Now, for this last part of the problem, where they ask us to locate a point C on the ground from O, where the force imparts 0 moment, really all that you're looking for is where the line of action for the force crosses the horizontal ground. That's really all you're looking for. So this is point C. And you know that's the point you want because any point on the line of action for a force has no moment made by that force. So this is really all we have to find. Now, if you will restrict yourselves to looking at the triangle that is formed here. So this is the line of action sort of as the hypotenuse. And I have this base, and then I have this height. This becomes a very easy problem because the slope of this large triangle that I've drawn has to be the same as the slope of the force. So I'm looking for some distance here that is d. And so the total base here is d, and then 36 plus 28, because that's the total amount of inches that I have to get from C all the way out here to this point of application at A. The height of this triangle is 10 feet, which is 120 inches. And so we'll just match slopes. Slope of the force here is 4/3. Okay, you could put base over height. It doesn't really matter. I'm going to do that. I'm going to put 3 to 4. And that has to be equal to the base here, d plus 36 plus 28, and then divided by the height of 120. And if you'll solve this out, you'll find that d is equal to 26 inches. So the point is 26 inches to the left of point O. That's really all you have to do for this problem. So just to recap, we broke the force down into vertical and horizontal components here, 3/5 F and 4/5 F, utilizing the slope here. Then we looked at point B, moment around it. Vertical force was clockwise, horizontal force was clockwise around B. Around O, vertical force was still clockwise, but the horizontal force was a counterclockwise. And then to find this point on the ground, we simply looked at the slope of the force and extended its line of action till this intersection point, and really just used similar triangles in order to solve for that distance d. All right, that's it for this question. A good question with a lot of basic principles involved here.